I have two material goals because I am a material girl in a material world, the material being physics, of course. I have two material goals to give, and then the rest of the time is I wish to do example problems, homework, plug in numbers, and see, get a feeling for amounts, magnitudes. As I have frequently told y'all, getting a feeling for how big should the answers be can really help you avoid silly mistakes. So we're going to start by talking about capacitance because we finished like 1 inch shy of this concept of capacitance. Let me remind you that yesterday class I presented a second scenario, the scenario of charges spread out not at a point, the point charge model, but over metal plates opposing each other. And for the point charge model, we have KQ over R squared electric field. Deja vu? Sound familiar? Whereas for the capacitor, parallel plate capacitor model, we have the electric field does not depend on position at all. As long as you're within the plates of the capacitor, it's the charge on the capacitor divided by the area of the plates of the capacitor times a constant, epsilon naught. Okay, so we have also spent a fair amount of time, namely half of last lecture, trying to get under the skin, trying to master the idea of electric field versus voltage. That connection is vitally important. I deduced that connection from the work energy, from the work energy relation, from the definition of work from before. I recognize that work is not a popular, that whole energy module comes at a time in the 111 semester where many people are exhausted in the mastery of work. If you've forgotten it, I understand. Hopefully, in the applying crap section of today's class, we'll get a chance to hit on the most important parts of that. If you plug in equation into equation, we get a result. The voltage across the capacitor is QD over A epsilon. Now, there are two things that I was asked about after the 4:30 class in this. One is, what the heck is D? And the other is, where's the minus sign? Yeah, right? The electric field versus voltage equation has a relative minus sign. And delta X turns into D, what the what? And the simple, let me answer these one at a time. The simple reason the minus sign goes away is because a capacitor is a common device that you buy for 12 cents from Mouser.com, comes in a little package, and you never, ever need to care about what the electric field's direction is inside the sucker. You don't use it in that fashion. So we don't care about whether the electric field points from positives to negatives, as it does. We don't need to care which side, well, that's all we need to care about. Which side is a positive voltage, which side is a negative voltage. That's easy to track. So we look at the magnitude of voltage and interpret the magnitude of voltage as whatever side has the positive charge is going to have the positive voltage. And I don't care about the fact that the voltage is decreasing in the direction of the electric field. Okay, so given that, I drop the minus sign. I take the absolute value and say I'm going to interpret the sign of the voltage based on the circuit rather than the physics of the electric field. The delta X turning into D. This, I go back to showing the picture of the sketch I made of a capacitor. Here's a sketch of a capacitor. It's two metal sheets of equal area A, separated by a distance D, and you smear some plus and minus charge over these. Okay, I ask you this. I put charges on the plates. Which way is electricity active? Which way does the electric field point? I've got, say, pluses up here and minuses down there. Does it make sense that the electricity, the electric field, the push and pull of electricity is from one plate to the other. That is the direction of the electric field. And as I just said, you don't actually need to care about the fact in this case that it's downward rather than upward. It's vertical. If I go from one plate to another, that is the relevant distance moved that makes an electric field build up into a voltage. That was the whole deal of half of yester class. That we go along a field line or opposite a field line, there's a change in voltage. If we cut across the field line, voltage does not change. You move horizontally along the capacitor in this picture, there's no change in voltage. But like there's nothing, the wires aren't connected to the left-right side of the capacitor. There is no left-right side of the capacitor. So that's why I use the distance between the plates, because that's the distance along which you would look of a field line to accumulate field into a voltage. And anyway, that's where the wires are connected to, at the top and bottom of the capacitor. So I hope it does make a little bit of sense that the relevant distance for E delta X is D. You'll always be given A and D, by the way. This is properties of how you manufacture the capacitor. Either that, or I would give you everything needed to solve for A, everything needed to solve for D. I think that's homework problem 8, actually. Solve for plate separation. And, or is it side length? Whatever, we'll solve for both in practice. The meaning of delta X turning into D, you would be given D or asked to solve for it as the only unknown variable. It's a property of the physical manufacture of the capacitor, just like length and cross-section of a resistor. So we get the voltage across the capacitor is Q, and let me separate this out as Q times D over A epsilon, not. And I'm going to identify the two parts of this. There's the Q part, and there's the rest of it, D over A epsilon naught. Let me think for a hot second about the difference between these terms. What's the difference between the charge on the plates and the shape and size of the capacitor? Well, the charge is an electrical property, and the shape and size of the capacitor is just how you manufacture the sucker. You don't change the shape and size of almost any capacitor that I could think of. So this is set, this is fixed, this is constant. You build it and it's done. This depends on what you're doing electrically to the dude. Okay, so I am going to define the ratio of the electrical quantities, just like I once defined voltage divided by current. I define the ratio charge to voltage as the capacitance of the capacitor. Well, let's plug in this formula. If I've got V equals QD over A epsilon, if I plug this into the formula, what do I get? Capacitance in this example for the parallel plate capacitor is charge over QD over A epsilon. Oh God, a fraction. Simplify. Let me see if you can. Practice your algebra rather than nodding along as I do it. Google question E. Simplify this expression for capacitance. You have 1 minute. You may help each other. And again, I'm asking you to simplify this fraction. Your task at the present is to take this fraction and simplify it. Okay, let's do this. If I've got a fraction downstairs, I can simplify by multiplying top and bottom by the reciprocal. Or you could say that when dividing by a fraction, the downstairs flips. Either way, this turns into, and what do I get when I got a Q upstairs and downstairs? Pew pew. My final expression for the capacitance of a parallel plate capacitor is A epsilon naught over D. I will note there's more than one way to make a capacitor. You can make a capacitor with a tube inside a tube. You can make a capacitor with 2 point electrodes near each other. Actually, every arrangement of two capacitors that aren't directly connected, every arrangement of two conductors that aren't directly connected can be viewed as a capacitor. Some are better than others. Some are more effective than others. This is one kind of capacitance, capacitor's capacitance. I want to emphasize particular versus general. Charge per volt, that is the universal, that is the definition, that is always true. Capacitance is always charge divided by voltage. For a particular scenario, I have got a given capacitor. How do I find its capacitance, other than looking at the fact that it's printed on the side, is I multiply its area by 8.85 10 to the minus 12 and divide by the distance between the plates. Bam. That's always true. This is true in particular cases. Let's take an example. Let's take a moment to do a couple of examples. Do you guys know what pico is? 10 to the minus 6 is micro. -9 is nano. It's the next one down. 10 to the, what, 4? They're always they're always multiples of 3. 10 to the minus 12. Pico, oh, is that what you said? I heard 4. Okay, pico is 10 to the minus 12. A very, very common capacitance value is 10 to the minus, is to measure the sucker in picofarads. So I challenge you as follows. Here, find the plate size. I'm going to have you manipulate this formula a smidge. That is to say, area of a parallel plate capacitor with 360 picofarads of capacitance. I didn't define. Big F is measured in farads, F-A-R-A-D, and the symbol is capital F. Farad. This is named after Michael Faraday, great experimenter from the, oh God, 1800s? Okay, so 360 picofarads, which is to say 360 times 10 to the minus 12 of the base SI unit. Okay, we're going to find the plate area, plate size. Find A for a capacitor with 360 picofarads of capacitance if the distance between the plates is, what is the actual practical value? About a millimeter. This will be Google question F. Plug in numbers. I will also remind you minus 12. Yep. And I'm going to ask you, G, how much charge does this capacitor hold when subjected to 12 volts? Okay. Use the formulas. Pluggy chuggy. And watch your units, y'all. You cannot ignore the milli and the pico. Also, more than half you asked for more practice problems? Okay. In the suggestions, you got it. Sorry, optional? Well, what do I use class time on? So would putting that in Pearson be best? Would putting that in an optional quiz that week be best? Would you like me to spend longer in the class? I can't spend longer in the class. That's what we do all class. In what form would you like that? Just to download, other than the practice exam. Okay. You want a longer practice exam, basically. Okay. Okay. Well, I'll give you two practice exams. There we go. Sure. Okay. But you don't want it through Pearson and you don't want it through Canvas. That's okay. 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 Hmm. I do. I do. Yeah. Because there are students that aren't in Tempe, that aren't in West Labs. Yeah. Those are posted on Canvas in the file section. I will point that out and make a bigger deal about it. You didn't know it. Okay. No worries. I don't usually make a big deal about it, but I'll point that out again. On the where? Yes. Oh, look, they're all like the beginning of the alphabet. How did I never notice that in 20 something years of doing physics? A, C, D, epsilon. Where's B? There's actually a kappa too, hiding. I've got two sig figs here. Oh, did you get it? Yay! Okay. I've not been teaching. I'm not going to hammer on it sig figs. You mean you didn't round? 0.041. Okay. Any way you want to write it. I have not been making a big deal about this, but please, please, I think that it will actually behoove you, given how many different quantities we've got, always put the units. Whenever I ask you a numerical physical quantity, number, space, units. That'll also help me track whether you're thinking about what you found and what it means. Sorry? No. Where's the seconds? Square meters. Yeah. Meter squared. Follow up to this, by the way. I don't feel that necessarily uh, square meters is something that people have a great intuition for. Google question H, can you find, suppose this is a square. What's the side length of a square with this area? I feel like people have a better feeling for single dimensions than areas. So Google question H, follow up. Here's the answer and the solution path for how to find the area of the capacitor plates. Now I challenge you to find the side length if this is a square. This should be a fast one. Mhm. And I didn't answer G. And so many people got H right, which means that F must be right. Let's see about this. Oh, my sweet baby Newton. Except for people who are mixing up what answer goes where. I'll take it. Good, good. Let me pause for a second. Let me pause for a second to have a chance to reflect on this. Um, these values for capacitance are entirely typical for a physical capacitor in the 1960s era that I did that I like to mess around with in my personal hobbies. 1 millimeter plate separation is actually a little bit fat, and 20 centimeters on a side is huge. This would usually be folded into a smaller area. You can use multiple plates stacked one after the other to make it to fit it in a smaller region of space. But this is actually these are sane values here. You might have an entire cube of stacked plates, as big around as my hand. They're kind of cool. Okay, now at 12 volts, entirely typical for voltages. God willing, you've seen scales of voltages to get a feeling for this. Nano amps, nano coulombs worth of charge. Again, I made a deal about this before. Coulomb is a huge amount of charge. Nano coulomb is entirely a reasonable amount of charge to have in a practical electronic example. I'd like to take a second. Oh, these are all entirely plausible, what? Entirely plausible exam questions, quiz questions, whatever. I'd like to take a second to give some follow-ups that will make you think about the meanings of these quantities that could also be on exams here. And then we'll hit on, what'll we hit on? We'll hit on finding the charge of point charges briefly. But I don't want to go on without having seen at least a couple of these. I challenge you, we have an example of a given capacitor. It's a square of 20 centimeters by 20 centimeters. It's about 20 centimeters by 20 centimeters. The plate separation is, as I said, about 1 millimeter, 360 picofarads, 12 volts, 4.3 nanocoulombs of charge on it. What would happen? What would happen if I do the following changes? I'm going to take this capacitor out of the circuit, remove the capacitor from the circuit, and then I'm going to screw with it. I'm going to mess with the capacitor. It's not connected to the circuit anymore. I'm going to halve its plate area. Shing! Take my katana and cut it in half. What would happen? What would happen to the capacitance? I don't want you to rerun the numbers. I want you to think about think about the quantities and the formulas involved, and don't use your calculators. Think about it and look for the answer with your heads. Again, what would happen to the capacitance if I take the capacitor and cut its plate area in half? Not the plate side length, the plate area. Google question I. Can you reason about this? What would happen to the capacitor's capacitance if I slice it in half? Let me be precise. What would the new capacitance be if I halve the area? Find the value. Find the value in picofarads. If thou must, you can check your answer with a calculator, but I would really like it if you would at least make a prediction. And remember that making a mistake on the Google form takes away no points. Give me your thought. Show me what you're thinking by making a prediction. And I'm going to call that time's up. I think that it is very important to be able to multiply and divide numbers. Yeah, that's great. Okay, good. But I think it is freaking just as important to be able to go around and think about mathematical quantities without relying on having a calculator in your pocket. Calculators suck. I hate walking around with one. Okay? You won't want to use Desmos for everything in your life. So please reflect on the following. I can rewrite A epsilon over D as A times epsilon over D. Doesn't matter the order I multiply and divide by, as long as numerators stay not downstairs, denominators stay downstairs. If I've got C equals A times epsilon over D, and I want to reason about proportions, this doubles, this halves, this quarters, this whatever, I can imagine that every other quantity in the algebraic expression stays the same. I mean, it does. If I'm saying I just change A, then epsilon naught, that's always a constant, and D is not being stated to change. So I'm just going to ignore him. Any multiplied quantities, you can rely on this. This is always true. Any multiplied quantities, when reasoning about ratios, stay the same. So I can say then simply C is proportional to A. What does proportionality mean? If I plug in, instead of C, I plug in 2 times C, I would get 2 times as much A. If I plugged in half as much A, I would get half as much C. I hate multiplication with my calculators and stuff. Well, like, I don't multiply in the first place. That's why I adopted. Hey! You all get it. Good. The non-silly point is, let's start reasoning about ratios and proportions and not being a slave to your freaking calculators. I see that if A halves, then C must be half as great, assuming the other quantities stay the same. This is called direct proportionality. I say C capacitance is directly proportional to the area of the plates. Okay, now I want you to think for a second, reason about this. Plug the capacitor back in. To the battery circuit, the battery, and just forget that there's potentially more than one thing. What is the new voltage? On the capacitor? Should say across. And K, what is its new? What is its new charge? And I challenge you to think clearly about these equations. C equals A epsilon naught over D. Oh, that's so messy. And I define capacitance as charge divided by voltage. You're good. For the sake of grading, please give me a value. Number, space, unit. Grading. We halved the plate capacitance, halved the plate area, and found the new capacitor is 180 picofarads. And now I'm saying, yeah, we had a 360 picofarad capacitor to start. If you cut it in half an area, you get half the capacitance. Now I say, if I reattach the capacitor to the battery, what happens? Does the voltage change? Does the charge change? If I have half as much capacitance, so what? Huh? Spoilers. Yes, you're right. And people are getting it right. Oh, that makes me happy. I just love it when you guys get it. Again, please give me a number. Don't tell me voltage increases, decreases, doesn't change. Give me a number. Blank volts. I will remind you that you encountered a very similar problem about changing the resistance of a resistor as the last problem on your exam. Okay, give me your best shot. 1 minute left. You. Oh my goodness. Okay, I'm going to call that time. From the last exam, does the battery change when I change the resistor? Does the battery magically become a 4-volt battery? No, 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 no. The point of a battery, how I originally described, not quite defined a battery, is it does its best to provide a constant voltage. Changing the capacitor's capacitance changes the capacitor stuff, but it doesn't change the battery. So the battery will still provide 12 volts. Google question J, 12 volts. I have changed the plate area of the capacitor. I've cut it in half. I now have 180 picofarads of capacitance. That means that I didn't change voltage. It doesn't affect the voltage. It's still 12 volts. Okay, so in reasoning about these quantities, you have to think, well, what changes, what stays the same? And you can't just think about one equation. If I've got C equals Q over V, those are three quantities, three different quantities. You cannot just guess this changes that, this changes that, this changes that. You have to reason about what changes what. So voltage does not change. I'm going to hold him constant. I'm going to say this is a constant multiplication or division. Capacitance is, again, directly proportional to charge. If I halved capacitance, I halve my charge. Final answer would be what? 2 nanocoulombs is what I said before? 2 nanocoulombs. So question J, 12 volts. Question K, was it 2 nanocoulombs? Was it 4 before? Right? Whatever, 4.1. So 2.1 now. Okay, last question before we go to the voltage of point charges is I ask you this. Suppose I leave the capacitor, I'm sorry, I take the capacitor off of the battery now. I'm going to remove the capacitor from the battery. It is no longer connected to a constant voltage source. Then I screw with the capacitor again. I make any change to its area or distance between the plates. I just want you to tell me what can change now. Can charge on capacitor plates change if it is removed from a circuit and then the dimensions screwed with? Can voltage change if I screw with the dimensions while it is separated from a circuit? What is your prediction about the nature of an isolated capacitor? Oh, God. This is not just what does the equation say. You have to think about a capacitor is made up of two metal plates separated by an insulator. What do you know about the nature of static electricity? Please, it. There are like 15 things that it could mean. You have to be more specific. Tell me what it means in your head. I cannot tell if you are right or wrong. You okay? Okay, good. You got a checkup at that length of time? Wow, they're a fast doctor. I've had doctors like that. Zoom in, zoom out. That's good. It's good, Selena. Yeah, yeah. No, I get it. Okay, one half a minute. I really want to not race through the last one. Oh, energy. That's true. We haven't talked about that one yet, though. Again, one last time. I take the capacitor off of the battery. I change its area. I change the distance between the plates or something. I don't know. Does voltage change? Can it change? Does charge change? Can it change? Okay, time's up. One correct answer is if I screw with A and I screw with D, C must change unless I do the same thing proportionally to both A and D. In general, you mess with the physical dimensions of the capacitor and the capacitance will change. Okay, so I just look at this equation. There is an equation for capacitance and it contains the physical variables. Okay, now let's think about the other one. If I change the left-hand side of that equation, if I change the left-hand side, the right-hand side must change somehow. So can charge change? Can voltage change? Can they both change? Well, what do you know about static electricity if I've got two pieces of metal that are insulated from each other that aren't connected to anything? Can charge teleport? Disappear? Multiply? Charge is fixed now. Charge cannot change because you have removed it from any way that that charge can flow on or off the plates. Yeah. Static electricity. If there's no conducting path and you don't take a magical wand and add or remove some charge, the capacitor's charge is fixed now. Well, if the charge cannot change and capacitance changes, what can you deduce about voltage? If I change the left-hand side and this no changey, this must change. If voltage changes, does that mean that the electric field changes? How's the voltage related to the electric field? What's the relationship between voltage and electric field? V equals E times D. V equals ED, remember? Remember? Yeah. Okay, so if I know that voltage changes, do you know that electric field changes? Not necessarily. What if you're changing D in the same way? What if changing D is Y, everything else is changing? You don't know for sure whether electric field is changing inside the... No, I'm so sorry. I can prove if I look at the equation for electric field in the capacitor where we started, charge over area epsilon, charge over area epsilon naught, Q over A epsilon naught, right? As long as the area is not the thing that is changing, and I know charge doesn't change, if I look at this original equation, I should not say math. Oh, for God's sake, where am I? Here. If I look at this original equation, and I know that the area is constant, I've deduced the charge cannot change, then the electric field is absolutely constant. So if the area isn't changing in the isolated capacitor, the distance must be. We're going to talk a lot more about How does this affect that? If this doubles, if this triples, does this quarter, does this multiply by 9, whatever? I consider this to be one of the biggest skills that's actually useful past the semester for the rest of your life. Being able to reason about quantities without a calculator. How does this affect that? Okay, real fast. We are almost out of time, so it's got to be fast. Let me do your homework problem. Systems of charges. And there's nothing to it. There's nothing to it at all, is the short answer. I don't remember the numbers, but I give you a test charge here, and let's say I've got 4 meters separation there, and 3 meters separation there. And I'm going to give you charge A, charge B, and charge C. How about I make up some numbers? Charge A is 6, charge B is 7 coulombs, 6, 7, and charge C is negative 4 coulombs. The test charge is, I don't know, 2 coulombs. L, negative 2 coulombs. Oh my sweet baby Jesus. Dr. Tucker only talked about 2 charges at a time exerting a force on each other. How the hell can I find the voltage or the energy of the test charge? Well, here's how. You do it 3 times an atom together. That's all. Energy of a given test charge and voltage at the position of a given test charge, you just add up the individuals. There's nothing mathematically to this. So in this particular example, let's plug in here. The voltage, say, because of charge A. What's his equation? Capacitance over, no. What's the charge? Point charge voltage. And I need to give this to you. We talked about the capacitor so long. Here is the charge of the voltage of a point charge equation. Oh my God. I apologize. Here we go. Misremembering the order I do things in. And let's talk about the meaning of these. They're exactly the same as K, Q, and R was before. Yes. Nope. That's electric field. This is voltage. Very important. You got to keep them straight. Voltage field, FU, EV are all intimately connected, and all 4 are going to have slightly different equations. Voltage, KQ on R. Energy, KQQ on R. Electric field, KQ on R squared. Force, KQQ on R squared. I suggest strongly, learn 2 and learn the connections between the rest. For instance, this is one I personally memorize. Voltage is KQ on R, and the electric field one, KQ on R squared. If you know force is QE, and you know energy is QV, then you don't need to memorize the other half. Okay, so the voltage due to A, KQA over RA. Voltage due to B, KQB over RB. Voltage due to C, KQC over RC. The total actual voltage, you'll never believe this, is you just add the freaking suckers up. That's it. That's it. There's nothing to it. So let's do this. Let's plug in some numbers. I gave you ridiculously large amounts of charge. This should be a huge, stupidly huge voltage, but let's do this. Plug in, and let me ask for the individual parts. Google question M, Google question O. I can alphabet Google question M, N, O, and Google question P. Give me numbers, if you can. I'm such a big silly. K is 9 billion. Again, if you've forgotten. 9, 10 to the 9. Six times 9, 54 divided by 2, 27 divided by 2, 13 and a half runs to 14. What? You don't like? Am I wrong? Did I get what? What's the distance of a diagonal? If I give you the side lengths of a rectangle, how do you get along? Break it into a triangle. Two triangles, I suppose. 3, 4, 5. You have to interpret. What is the distance from what to what? If I'm talking about voltage of B, I asked what is the distance from B to where I care about. If I'm asked about the voltage of C, I look at charge C. How far are these two apart? Oh, yeah? You like? I should have carried guard digits. That hides the one. Whoopsie. Let's see who got there. Yay! I got some failures in the 10 to this. Some, but mostly not. Great, 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 great. Okay, let me point out one thing here. One potential point of confusion that I will get asked about, inevitably. When I said electric field calculation, I always encourage you to plug in positive charge and then think about which direction would a charge get pushed, away from positives towards negatives. Figure out the direction of electric field by sanity and reasoning. Voltage has no direction to it. Voltage is a positive or negative number. So there's no really reasoning about it. You can get some experience with this, but this you could just plug in plus or minus charge. Distance is always positive, K is always positive. You get plus or minus voltage. And I want to talk more about what negative voltage in this context means next week. Same bat time, same bat place. Last chance for questions? That should be everything you need for now, and I think we're in a good place. Hooray! Another week bites the dust. That's recording, right? Right?